Okay, 123 class, let's look at your exam. And let me go through this 5, and maybe this will be a good learning opportunity for you, and maybe you can see what you did right and correct what you did wrong. Let me start with this first one. Hopefully you see the prism here and Snell's law. It says a light wave traveling in air and parallel to the hypotenuse of a 35, 55, 90 prism strikes the short leg. The short leg has a length of 2.5 centimeters, and the light ray hits the prism a 0.5 centimeter from the right angle. All right, so here's the light ray parallel to the hypotenuse. That tells me this is the 90 degrees. And you can kind of see that this is not drawn to scale purposely, because it says here that the traveling in air parallel to the hypotenuse strikes the short leg. So this is the short leg, and the short leg then would go opposite of the smaller angle. So this must be the 35 degree angle, and this must be the 55 degree angle. Okay, and then this short leg has a length of 2.5 centimeters. So this whole thing is 2.5 centimeters. And the light ray strikes the prism a 0.5 centimeter from the right angle. So coming down, we're looking at a 0.5 centimeter. So coming up from the bottom, we're at 2 centimeters. And so this is where the light ray strikes here. Okay, if the glass prism has an index of 1.6, so it's probably that lead glass we were using in lab, it says carefully draw the path of the light ray takes through the prism, and then B, at what angle from the normal does the light ray exit the prism? So we've got 2 questions. Let me get to a clean piece of paper and maybe draw a little bigger prism here. Let me give it lots of space here. So that'll be the short side. And we already said this here would be the 55 degrees, and 1, 2, 3, 4, 5. The light ray would be hitting right about here, so that this distance is 2 centimeters, and up here to the right angle is a 0.5 centimeter. Then it makes a 90 degrees and goes to the longer leg. So 90 degrees. And so what first is going to happen is this refraction as it enters the prism. Of course, we call that Snell's law. And so let's run through the math on that. Of course, we know that n1 sine theta 1 is equal to n2 sine theta 2. So the 1s are where they enter. So we're starting from air. So the index is 1. And then we have sine of, okay, and so we need the incident angle. And remember, it's measured from the normal. So this right here would be a set of alternate interior angles. So that would be 55 degrees. So that would make this angle here 35 degrees. So the angle of incidence is 35 degrees. And it's going to go into the prism, which is 1.6. And then that's going to tell us what theta number 2 is. Okay. Now, we know it bends towards the normal because we're going from a high-speed area to a low-speed area. So it's going to angle down something like this. Now, let me not draw too much of it, because I'm not sure how much it angles down yet. I need to do the math. Because if it angles down quite a bit, it might go and hit the hypotenuse. If it only angles a little bit, it might hit this longer side of the triangle. So there's some thought I need to kind of do here, but let me grab my calculator, and I think I'm in radians mode. Yeah, so let me switch my calculator over to degrees, and then put in right here a sine of 35. Then I'll divide that by 1.6, And then I will take the inverse sine of all of that and get about 21 degrees. So 21.0 degrees. So this angle in here is 21. Now that can be helpful because if I draw across here where the ray would have continued to go, which is horizontal, note that, you know, this whole angle here would be 35. And so if I take 21 away from it, I'm left with a 14. Now, the reason I point that out is I was kind of curious how much this is dipping down, because I know, let me just draw a horizontal line up here and do alternate interiors. This is 35. So this side of the triangle is angling down at 35, and this line is angling down at less than 35. So if it was 35 or more, I know for sure it would go down and hit the hypotenuse. But given that it is under 35, and it's quite a bit under 35, it has a good chance, I think, of hitting this leg here. Although I need to reason it out and see if it does or not. And maybe the best way to do that is to kind of see how far, you know, as this comes down, how far horizontally does it go before it crosses this line. And if it crosses it beyond this point, then I know it must have hit this face. If it crosses before this point, well, then it doesn't hit this face or this side of the triangle. So let me do this. Looking at this right here being 2 centimeters, let me figure out how tall this is. This would be the sine of 55. So it would be 2 times the sine of 55. And so the height of this is 1.64. Okay. So I say that because if I were to think about this extending out, and again, I don't really know if it hits this face, but I'm going to draw it that way for a moment, and I might have to redraw it if it hits the prism, the hypotenuse first. But what I do know is this angle down here would be the 14 degrees. That would be these alternate interior angles. So the tangent of 14 degrees would be the opposite, 1.64, divided by this length. I'm trying to figure out where does it cross. So let me call that x for a moment. So 1.64 divided by tangent of 14 degrees is pretty far, 6.58 centimeters. So again, I'm thinking that it probably does hit here, because from this point over, it's 6.58 centimeters. And I need to check this number here to see if 6.58 is further than this point, but I'm pretty sure it is, just kind of looking at these numbers. So why don't I do this for a moment? Why don't I ask how far, and I didn't give myself much room here, but maybe I should ask how long is this whole hypotenuse? And then subtract off this piece, and that would tell me how far over it is. So I'm going to kind of do the same thing. I'm going to look at the actual triangle or prism itself, and then this is sine, because opposite over hypotenuse, yeah. So sine of 35 degrees would be the opposite, 2.5, divided by the size of the hypotenuse. I'll just call it h. So 2.5 divided by the sine of 35 means the whole hypotenuse is only 4.36 centimeters. And that's interesting because then I need to subtract this distance, which only makes this distance shorter, and this number is already smaller than that. So that answers the question. I don't even need to figure out that, although it would be just 2 times cosine of 55. But it would tell me that this beam is going to strike way out here, and I think that's probably part of the author's problem here, is setting it up that it strikes really high up here and turns only to 14 degrees, so it crosses the plane way out here, and therefore you don't have to work too hard to come to the conclusion that it is going to hit this leg first. All right, so now I can continue on. All right, so I would need to know then, using Snell's law again, what this angle is. And again, measured from the normal. This is the ray here. Okay, well, maybe the way to do that is to kind of look at this triangle here, which we know adds up to 180 degrees. And we know that one's 90. And this one angling down is 14. And remember, we could say that this is 55. We could either say that because these are corresponding angles, or we could say that because these are vertical angles. But what that means then is these two added together, 14 and 55, so that angle, and then that angle, 90 degrees, and then this angle, which I'll call that, say, beta, so beta, must equal 180 degrees. So beta would be 180, let's see, minus 90, minus 55, minus 14. And so we're looking at 21 degrees here. Okay. Which, of course, then makes this 69 degrees. Now 69 degrees is a pretty big angle. If you remember when we were doing our optics. Oops. Looks like that was out of the picture. So this is 21 and this is 69. When we were doing our optics and we were using glass, I believe we had a critical angle of 42. And this has a higher index. So the critical angle should be even less than that. So this tells me that this is going to reflect. So it doesn't exit. It reflects. And now it hits the hypotenuse. Now, I suppose maybe we could go through a little step here and convince ourselves. We can do this one of two ways. We could just, calculate the critical angle. And we know that the sine of the critical angle is the index it goes into compared to what it started in. And for any angle greater than that, it would reflect. So if we do that, right here it's going into the air, so that's a 1, and it's coming from the prism, and if I go inverse sine, we're looking at about 38.7 degrees. So clearly, like I said earlier, compared to our lab, that this is clearly much, much greater than the critical angle. So it's definitely gonna reflect. Now, even if you didn't notice it and you tried to do Snell's law as it tries to exit here, you would do something like this. You would say, okay, it's in the glass and it's striking it at 69 degrees. That has to equal going into the air, and then this would be the angle that it comes out. But this should get you into a mathematical nightmare because there should be no solution. It doesn't actually come out. So 1.6 times the sine of 69, then divided by 1. See, notice it's greater than 1. And so if I try to take the inverse versus sine of this, it's going to say error. What was this, about 1.5? Anyways, and so I'm just going to say no. there is no exit angle there. Okay, so that's kind of an important step also. So this problem, as you can see, is a bit interesting and a bit complex. You can't just simply know where it's going to hit. So the first step is real easy, yeah. But now it gets a little more involved. And knowing that it hit this face, well, it took a little thought. And then noting that it hit the face was a critical angle was important here. And so now we begin to ask right here where or what is the angle that it exits at. Now, since it reflects, and I don't have much room to write it, so I'll just mark it. We know that that is 21 degrees. And this angle here from the vertical, maybe I'll label it, might take some thought. But remember, this angle here is the edge of the prism. So that's the 35 that I kind of covered up right there, which makes this one right here the 55. So that must make this 125. Okay. Let me just check. Does that add up to 180? Yeah. So and that add to 90. Yeah. So that would be 55 right here. This one then would be the 125, and that would be the 21. So in other words, the incident angle, right, coming in right here, let me call it a theta, because I'm going to call it a theta 1 in a moment. But that angle plus the 125 plus the 21 is supposed to give me my triangle. And so let's hope that that's less than the critical angle. Otherwise, it's going to reflect off that hypotenuse too. So 180 minus 125 minus 21. Is 34. Okay, and 34 is less than the critical angle. So there's our answer to our path, and it's going to bend away from the normal. And so maybe I'll draw it in green. This would be our answer to part A, that the ray, oops, keep pushing this out of the screen. Sorry about that. But this would be our path then. So it would come in and turn towards the normal, but then do total internal reflection off the side of the triangle. Then it would exit because we're greater than the critical angle, and then it would exit. Now, I might have had this drawing out of the screen, so let me say this again in case you missed it. This angle here would be 35, and then these two have to add up to 90, so that makes this one right here 55. These two have to add up to 180, so that would make it 125, and that would be 21 because it's the reflection off of here. So there's the 21, and then these three angles, the 21, the 125, and the angle of incidence going into the hypotenuse, so I'll call it theta, would have to be a triangle, have to add to 180, making that incident angle 34. 34 being less than the critical angle means it's definitely going to exit, or at least a percentage of the ray will exit. Okay, so the last step to do then is to apply Snell's law a second time, as we are exiting the prism. So starting in the prism, 1.6, and the incident angle we just said is 34 degrees. It's going into the air, and we can get the theta 2, and the theta 2 is measured from the normal. So that's good. We don't have another step because part B says at what angle from the normal? At what angle from the normal does the light ray exit the prism? What it doesn't tell you and help you with is whether it exits from the hypotenuse or the long side or the short side as it ricochets around in here. But we've decided that it exits the hypotenuse here. All right, so that being said, let's solve this. And grabbing my calculator here, 1.6 multiplied by the sine of 34. And now finally, taking the inverse sine of that, and we get about a 63.5 degrees. Yay! And so there is part A, drawing it, and part B, what is the exiting angle. But, as you can see, it's not all that simple, and it takes a lot of work to get there. And that could have taken you your allotted 25 minutes. It took me 21 minutes although I was talking a lot about it, so hopefully it took you less than that. But kind of makes sense here. All right, let's move on to number 2. Okay, number 2 also is one of these problems that has a part A and a part B. And again, part A real simple, but part B, it's got some challenges in it. But it says here we have an 8 centimeter tall upright arrowhead right here, and it's 25 centimeters from a convex mirror with a radius of 50. So that means the focal length is half that at 25. And remember, with a curvature this way, got to watch our signs here. This is our sign convention. And so maybe if there's anything that might be challenging, it would remembering our sign convention. But so we're looking at a negative focal length of 25 for this mirror. And this says, how tall is the image of the arrowhead as seen by the person? So the person's over here and is going to see a reflection. So they're really asking the image. How tall is the image? And then, of course, what direction does the image of the arrowhead point? So it could be up or down. And how far from the mirror is the image? So there's 3 parts to this, but it's also, I think, pretty straightforward, at least compared to what it's going to get in part B. So starting with 1 over P plus 1 over Q is equal to 1 over F, I can say that the object distance is 25, so the arrowhead is 25 from the mirror, trying to figure out where the image is, and the focal length, as we just said, is a negative 25. So grabbing my calculator, let me put in a negative 25 and take its reciprocal. Let me move this over so it's negative 25 and its reciprocal. Hit enter, reciprocate that. And so we're looking at a Q that is a negative 12.5 centimeters. So what that means then is an image will be formed over here on the virtual side of things. So I guess I've kind of answered this, how far. Maybe I'll just put right here how far. And so the distance is 12.5 centimeters. And I guess it would be fine to answer it as a positive as well as a negative. Makes sense. I'll take either one when I start to grade these. But the question just asked for distance. Now, hopefully you weren't careless with your sign when it came to the magnification, because it's the minus Q over the P means we have a minus of a minus 12.5, and the distance was 25. 2 negatives make a positive, and that comes out to be 1/2. So the magnification is 1/2. So if you set that equal to the image height over the object height, where the object is 8, you're looking at a height of 4. And notice it is a plus 4. So the height of the image is 4 centimeters. I think that was another part of this question. Right? It says, how tall is the image, so it's 4, what direction does the image of the arrowhead point? And since the magnification is a positive number, it would be up. And so if I say direction, it would be up. So there's the answer to part A, the 3 pieces: how far, how tall, and what direction. Okay. So again, that's just kind of a simple plug and chug into this, but well, a little more than that. We've got to interpret our numbers and watch our sign convention. Here's where it gets really interesting. What if we put a convex lens with a focal length of 10? Now, we probably should ask ourselves, is it a positive 10 or a negative 10? But it's convex lens, so it is a positive 10. It's placed 12 centimeters to the left of the mirror. So we're looking at a lens that would go right about here, so that this distance is 12, of course, making this distance 13 for a total of the 25. Okay. So convex lens with a focal length of 10, so I'll put F equals 10 down here, is placed 12 centimeters to the left of the mirror. And then the same 3 questions. How tall is the image? What direction does the image point? And how far from the mirror is the image? Now, what's interesting about this one is conceptual. That the light would go through the lens and be manipulated and then hit the mirror. So the first thing to recognize is, how do you do a optics problem where you have multiple lenses or multiple mirrors, or in this case a lens and a mirror? And the answer is the light gets manipulated from the first one to form an image, and then you can just treat the image of the first one as the object of the second one. So you don't really need anything fancy when you have 2 or 3 or 4 or 5 lenses. You just do one lens at a time. So let me find the image of this first one, and that will become the object for the mirror. But here's what's interesting about this one, is that then the light will bounce off the mirror and go through the lens again before this person sees it. So it's actually a 3 optical element problem, because the light goes through the lens, then bounces off the mirror, then through the lens again. And so we need to answer this problem with a 1 over P plus a 1 over Q and a 1 over F, not only for the first case, but maybe I'll give myself a little bit of room. But then the light has a second optical element, and that would be the mirror. And then it does it yet again, going the other direction through the lens. So this could be easily overlooked, that third step. And so I hope you didn't. All right. So I'll start with the first step, the 1 over P. And so this arrowhead is now 13 centimeters away. And let's find the Q. And remember, the focal length is a 10, we just said. So grabbing my calculator, I would have 10 reciprocal minus a 13 reciprocal, and reciprocating that means we're looking at a positive 43.3 centimeters. Let me call it magnification number 1, which, remember, is a negative Q over a P. And maybe I should call all of this number 1, 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 because there's a number 2, number 2, number 2, and number 3, number 3, number 3. Okay. So if I take the negative of that last answer and divide it by the 13, we get a negative 3.33 for the magnification. Now, I can't really draw it on this little sheet, but that hopefully does make sense. Let me ignore the mirror for a moment, because the focal length of this lens would be, right about here and about here. And we said many times as we were doing these problems that if you have an object that is between one focal length and two focal lengths, it will make a magnified upside down real image over here. So the light's going to do something like this. And this is where the image would be formed. If it didn't hit the mirror. We got more to talk about here. But if it never hit the mirror, that's what it would look like. In fact, maybe I should kind of draw that. Maybe I'll draw a small arrowhead and give myself about 3 centimeters to the focal length, about 10 centimeters to the convex lens, another 10 centimeters. And if I was drawing rays, it would go something like this. And so I'll draw a dotted line to be that lens. And so we're looking at something that is now inverted and about 3, how many times? 3 1/3 bigger. Oh, good. And my drawing kind of matches that. So that's what this first step is saying. Of course, as you know from the problem here, at about 12 centimeters away, there's a mirror. So maybe I should put right here lens mirror. So the light actually hits the mirror and bounces back. So it never really forms this image. Again, this is just a good way of thinking about what would have happened. So coming back here, I can say then that I need to put in my object distance. And this is what's going to make the problem hard. Remember, this is going to be then the virtual object. So the image of the lens, that's this, becomes the object for the mirror. But the weird thing is the object isn't actually formed until after the light hits the mirror. And so that's our negative distance. And if we said that this was 43.3, so this right here is 43.3, but we subtract off this 12, 43 minus 12 makes a 31.3. So my object distance is 31.3, and it's negative 31.3. So that is my object distance. Now I'm looking for my image distance. Okay, so where is the image formed? And I have a focal length of that mirror, which we decided already was a negative 25. So where is image number 2 formed? All right, so grabbing my calculator, I guess I have a negative 25 reciprocal. Bringing this over makes it a plus 31.3 reciprocal. Hit enter, reciprocate that, and we're looking at a negative 124.2 centimeters. So it's a long distance away. 25. Yeah, okay. Just wondered if I put it in right here, negative, because that's a big number. And what would it mean? Well, let's go to the picture, but let me do a magnification here. And so if I take a negative of that number, so negative of the last answer, and divide it by the p, which is a negative 31.3, we're looking at a magnification of almost 4. -397. So the negative means it's inverting it, and the, of course, greater than 1 in terms of absolute value means it's making it bigger. But the negative Q is quite interesting. I didn't really see that coming. Maybe we can see it in our diagram. But that means if this is the mirror, the negative Q is way out over here somewhere. So the image now from the second optical element, the mirror, is going to be way over here. It's going to be inverted. So this was already, 3 times bigger. Now it's going to be 4 times bigger than that. So it's going to be a big old thing way over here. And I guess that would make sense if we maybe did something like this. Let's see, the focal length of the mirror is 25, which is just shy of the 31. And if you wanted to try and draw the light coming here, the 2 rays you would need to focus on is the one going parallel to the mirror. Okay, so that would be this one here. And it would bounce off as if it came from that focal point. So this ray goes here, then it goes straight, then it hits the mirror and bounces off like that. The harder one to draw here, especially because the number is so big, let me maybe use the back side of this so I can draw off here. But you want to draw the one that goes, towards the focal length. So I'm going to have to extend my mirror like way up here and say that what would happen is there would be a ray that is coming down and converging here. Remember, all the rays would converge here. I only drew 2, so they hit this lens and then converge. These are the 2 I drew, but all of them would do that. So, like, I could draw this one. Now, this would be kind of useless one to draw, but what I know is it's going to hit the lens and then go right to this arrowhead. The one I want to draw is the one that would go to this arrowhead through this point after hitting the mirror, coming through, or after hitting the lens. So I should have extended the lens up, not the mirror. And so it would be the light ray that I guess would do something like this and then come angling down and go through here. And of course, now that it hits the mirror right here, it doesn't really go down. It bounces off as if it goes straight. And so if you trace this back and you trace this back, you're going to get something like very big, very far back, something way over here that I can't really draw on this scale here. I may need to start with these things smaller to get here. But at least I kind of get the idea now, and I can definitely see it in the numbers that this is going to be back here at 124.2 centimeters. So that's going to be the second image. That's the image of the mirror. And notice that it's right side up again because they've been magnified. Each has a negative. And so right now, like it's a little more than 3 and a little less than 4. So let me call that a 3 and a 4, 12. So this thing is 12 times bigger. Of course, now the light goes back through the lens. Now, these big rays that I drawn wouldn't go through the lens, but the ones that are going to come through here that would have gone there, that then go back through the lens, these are the ones that are going to make the final image and the part that can be easily overlooked, and that is step 3, that the light gets affected yet again. All right, so how far is the object here? Well, maybe coming back to our picture, because this is the 124.2, so here's the image from the mirror. It's now going to become the object for the lens a second time, and it looks like I've got another 12 to add to that. And the light is going in this direction, so that's a positive number. So if I add 12 to that, what's that? 134.2. 36.2. I knew that something didn't seem right. Yeah, 2. Yeah, okay. All right, so I have here 136.2 and a positive number. And I'm looking for Q3, and I'm at a focal length of 10. Now, before we do this last calculation, remember, kind of like we did the first one, where I said, keep in mind that if you're between 1 focal length and 2 focal length, you make an upside down larger image. Now we're much greater than 2 focal lengths, and so 2 focal lengths makes an upside down smaller image and real. So ultimately then it's going to be flipped again and smaller, and it's going to be real. So the final image is going to probably be right about there, taking this really big one and saying it's going to make a small one. But let's not worry about drawing the rays. Let's just do a calculation here. All right, so when I go to do a calculation, I've got my 10 reciprocal, and I will subtract 136.2 reciprocal, hit enter, take the reciprocal, and we're looking at about a 10.8. And again, notice it's a positive 10.8. Fits our drawing really well. That it's going to be out here just beyond the focal length. So its image after all three is very close to the original object, except it's going to look upside down. And then maybe we can even do here a magnification, number 3, because it would be a negative of the last answer, divided by this 136.2, and we are looking at a negative 0.792. All right, so I told you this was a pretty involved one here. And what direction is the image? And so it's the same 3 questions. Let's do now the total magnification, because it would be the 3 of these. So it would be a negative 3.3333 times a negative 3.97 times a negative oops, I wrote it down wrong. My apologies. It was a 0.07. It's right there. 0.0792. And overall, when it's all said and done, I have a negative 1.15. So it's only slightly bigger than the original object. In fact, we can now say the height of the image over the height of the object, and the original is 8. So if I multiply that by an 8, we are looking at a negative 8.38. And that right there answers 2 of the questions. I guess if I say the height of it, I'll just do the positive part of it, like I did up here in part A. So there's its height. When its direction, I'll say it is now down. So each one has been inverted. So after 3, it's totally inverted. And the question about how far might take a little more thought, because it says how tall, in what direction, and how far from the mirror is the image. So this number here, Q3 of 10.8, is a distance measuring from the mirror. So it's 10.8 from the mirror. Now the original object was 13, so in this picture the final image would be right about there. So that's 10, but remember it's another 12 over, so let me add 12 to this, and so it's 22.8 centimeters from the mirror. So got to ask our question, where is it from the mirror? All right, well, again, that was a doozy one too. That probably will take you your whole allocated 25 minutes also. So yeah, see, we're just under 50 minutes here. Okay, well, we still got 3 more to do, and maybe those will take 25 minutes each too. All right, let's move on here to number 3. Number 3 says, light of wavelength 645 nanometers passes through a pair of double slits that are separated by this much, and each slit has this much. The screen is this far from the double slits. If the intensity of the light is 35 watts per square meter at the center of the screen, what is the intensity of the light 1.3 centimeters from the center? All right. Well, this one sounds like the grand finale of our double slit. If you remember, we talked about the interference of the double slit and had something that looked like this for the interference of the double slit. Then we introduced in 38 the single slit and had something that looked like this. I'm going to write it as beta over 2 and beta over 2. And so this was our diffraction pattern. And the grand finale was it was both of these at the same time. And so I think this problem wants us to include both the effect of the interference from a double slit, because it makes it very clear it's a double slit and it gives us all the numbers we need. But I think it also wants us to do the diffraction intensity, because they give us the other piece that we need, which is the size of the single slit. So let me write the combination of these two together, and usually we do the diffraction envelope first. So this is really telling you how much light spreads out through the slits, and then this tells us the interference of the two. So we have to put in our numbers, and I'll start with this phase difference. The phi was the phase difference. Maybe I'll draw a little picture up top here, between two slits. And so we said the phase difference over 2 pi is related to the path difference over the wavelength. The path difference is d sine theta, and sine theta can be written as lambda over L. And if we then move the pi over here, we have then phi over 2 is then equal to dy lambda over L times pi. And it was the same logic for the phase between the first and the last. It's just that we had then an A And so that picture would look, maybe I'll put it right here. If we had a single slit and a screen, we would have the interference on the screen from the piece of the single slit that was here and the piece that was here. And so that would be the extra path difference of A sine theta. Whereas back here, this was the extra path, and so it was D sine theta. But everything was the same in the sense that we would have something that would look like this. Beta is to 2 pi, as path difference is to wavelength, which would be A sine theta over wavelength. And then we can replace sine theta with y over L. Okay. And of course, this is an open notes one, so probably don't take your time like me to talk about it or to derive it. Just punch these into your calculator here. All right, so let's get this phi over 2, and I'll do it in terms of how many pi's is it. So D is what? The double slits, they are separated by 0.45 millimeters. So there's D. Y is the distance up the screen, and that's what they say, 1.3 times 10 to the negative 2 for the centimeters. I'll divide it by the wavelength, which is 645 nanometers. And then also divide by the distance to the screen, 1.15. And by the way, notice I converted everything into meters. All right, so that's, if I hit enter, is almost 8 pi. It looks like it is 7.89 pi's. Okay. Now, I wanted to list it in terms of how many pi's, because looking at these two functions, and this one here would be the cosine, it repeats every 2 pi, and at 2 pi it's 1, so this is almost a 1. So we're somewhere on the screen where we're getting constructive interference between the first and the second slit. And it would be 8 pi, so 2 pi, 4 pi, 6 pi, 8 pi. So this would be the m equal 4 as we were labeling them on the screen. The center one being m equals 0, so then we would have a bright one at m equal 1, another one bright at m equal 2, another bright at m equal 3, and we're really close. We're just a little shy. We're not quite at 8 pi, but we're almost there. If we're kind of curious to where we are, we're almost to that point. And I hope you do get curious. Don't take the time during a test, but it's always good to read into these numbers, not just do the math, but to read the numbers here and say, okay, what do these actually mean? Now, let's do the same thing for the diffraction pattern. Of course, it's going to be a different number. And instead of typing everything in, because I did this, let me take what I have and divide it by the D, which was 0.45 millimeters. So when I divide it by D, I have just the Y, lambda, and L left over. So then let me multiply it by just the A. So I got rid of the D, and now I'm going to multiply by the A. And so the A is 0.065 millimeters. Okay, and hit enter. So this comes out to be a little over 1 pi, 1.14 pi's. Now again, this is kind of an important one, I think, to ask, because again, we've learned for the diffraction pattern, we get dark spots here at every multiple of pi. And we're not quite at a multiple of pi, but pretty darn close. And so this beta over 2, because sine of pi is 0, is at a diffraction minimum. So what these two are saying is the 8 pi here, it means we're pretty close to constructive interference between the two double slits. But sadly, we are also at a point where we are projecting little to no light because of the diffraction interference pattern. And so we're going to get very little light. So let's see what we do get. So calculating this, we've got the 35 watts that is down the center. We've got the sine squared of 1.14 pi's. We're also going to divide it by 1.14 pi's squared. And then we've got the cosine squared of about a 7.89 pi's. All right, so this should give me my intensity here. Now, I believe when we did that first problem, yeah, I moved it to degrees. Let me switch it back to radians, so that I would get something. Maybe I'll do these two separately for just a second. I'm kind of curious. So if I do sine of 1.15 pi's, I guess I would have thought it's smaller than that. Although I am going to square it, so it is going to get smaller. So yeah, okay. But let me also do this, 7.89 pi's. Oh, let me do cosine. Cosine of 7.89 pi's. Okay. But now let me square these. So let me grab that one and square it times this one here and square it. And so that would be the two of those squared. Oh, I needed to put a parentheses around that negative. Otherwise, the computer just thinks of squaring the number without the negative. Well, that would have just dropped the negative. So let me ignore that a negative, or let me get rid of it by doing that. Okay, so I think the number is still good. Times the 35, then divided by 1.14 squared, and also divided by a pi squared. Okay, so if I did all this right, and I'm not sure I like what I did. Let me just try that. 1.14 times pi. It's 3.59. You go sine of that number and square it. Okay. Times cosine 7.89 pi squared, then times the 35, then divided by, and I'm going to put it in parentheses this time, 1.14 pi closed squared. Okay. And so 0.438 watts. All right, well, maybe that seems reasonable. Yeah, I mean, that is pretty small. Yeah, I guess. I'm glad I did it a second time. Not sure why that was bothering me so much, but okay, I like that. All right, so there's my intensity. Now, let's go to B. And fortunately, it doesn't look like B is going to be the hard one. That one, A is the hard one. Because then this one just says, if the double slit and screen are now placed underwater, what is the intensity at this same place? So it's really the same problem, except we now have a smaller wavelength. And so all the physics is the same, where we're going to get our interference, we're going to get our diffraction, so we're going to have this factor, we're going to have this factor. Everything's going to be the same underwater. But the big thing is the interference has to do then with the wavelength, and that's what has changed as the light moves across here. So we could kind of start this by saying what we would have is we would have this D, this Y, this lambda, but this would be the wavelength divided by N. So, oops, pi. So we would have a D, a Y, a lambda L, and then we would have an N, and then a pi. And the same thing with the beta. It would have the A, the Y, the lambda, the L, and then there would be a factor of N, and then a pi. And so everything is nearly the same, except we just need to come back up here and multiply by 1.33. So let me do that. Let me take the 7.89 and pi and then multiply it by 1.33 and get 32.97 radians. And I won't even write it in terms of pies anymore. And then here, let me take the 1.14 pies and increase it by 1.33. And we are looking at 4.76 radians. And that way I can just do part B here by just putting everything in here real quickly. I might start, though, with the sign of it first. So let me go sine of the beta. And that'd be the last answer. So I'll just go last answer. Let me close that. Let me square that. Let me go then times the cosine. And this would be the 32.97. Let me close and square that. So that'd be these first two. Let me then multiply it by the 35. Now let me divide it by this beta squared, which is the last answer. So let's go last answer squared. And I get an intensity, whoa, really small. 0.00043. Wow. But now that tells me that probably one of these, 1.14 times 1.33, 1.5 pi. That wouldn't be the 0 one. Let's try this. 7.89. That's about an 8 pi times 1.33. How many pies is that? 10. Oh, 10.5 pies. So there it is. 10.5 pi. That's a cosine function. And so the fact that we're at a half pi means we're at a 0 place of the cosine. So we're going to get a dark spot here. It would be one of the destructive interference from the double slit. So very little intensity. We're almost directly on that dark spot. Really, really small. All right. So that's kind of how I would read the numbers. But again, don't take your time during the test. Just get these answered and move on. All right. Well, glad that one didn't take nearly as long. So in terms of pacing ourselves, I'm a little bit ahead. Let me throw that one off to the side here. All right. So next page here. So number 4, some interference. We have a small drop of alcohol, which index 1.55. It's placed on top of water, which has an index of 1.33, and the alcohol makes a small mound from the thickest to the thinnest part. And so I was kind of doodling here in my own mind earlier on and trying to draw the two reflections. And so if this is kind of the alcohol mound here, so here's water, 1.33. Looks like my pen is starting to dry out a little bit. Let me go to another pen, 1.33. Here is the alcohol mound. I'll give it a little bit of shape. But what's important here is to recognize that the light's going to come down and bounce off. And I like to put a little circle around it to say, look, it phase changed right there. It went from a small index to a large index. But the second ray, which is bouncing off the water surface, doesn't have a phase change because it's going from a big index, 1.55, to a small index. Now, the reason that's important is the way you analyze these equations. If you say you have a thickness T, the extra distance that one travels versus the other is 2T. And I usually start off and say if that extra distance is an integer number of wavelengths, and it would have to have wavelengths in the material, you would get constructive interference. However, if one of them undergoes a phase change, you would not get constructive as you first thought. You would get destructive. So that's where I begin. This would be then the equation for giving me the dark stuff on reflection. And then I can list the other 3 equations, like this one, 2t equals 2m plus a half lambda over n, would give me maximums on reflections. And then I can reverse those for transmitted light. But before I write all those down, let's just see which ones I need here. A small drop of alcohol is placed upon water. The alcohol makes a small mound. The thinnest part of the mound to the thickness part, to the thickest, the 18 dark, so I want minimum, and reflected. So that would be this equation. Yeah, so I don't need to write out the others. I didn't even need to write out that one. And so for this problem, I'm interested in this equation. Okay. Here is the wavelengths reflected off the alcohol mound. How thick is the thickest part? All right, so you can see that the first reflection, if I kind of draw the alcohol coming down to a small edge where it has almost 0 thickness, you would match this equation with m equals to 0. 0 thickness, m equals to 1. That means this edge right here, you would look dark. And it makes sense because there's essentially no extra distance traveled, but there is a phase change, and that's why you would have destructive interference. So the thin part of this mound would be dark. And then, of course, it would get bright, and then dark, and then bright, and then dark, and then bright, and then dark. And eventually, at the thickest part, it's dark again, and there's 18 of them. So if we were numbering them using our index m, well, I guess we'd say 0, 1, 2, ... and we would get to number 17 before we listed the number 18. So that's important to realize. 0 through 17 is 18 fringes. And so we need m equaling 17 here. And now we can solve for the thickness because we know the wavelength, 465, and I'm going to leave it in nanometers. And the index is 1.55. So here's the first part of this. This tells us the the thickness. So 17 times 465 divided by 1.55. Oops, and I must have hit something wrong. Oh, got a comma in there. Let's try that again. 17 times 465 divided by 1.55 gives me, looks like 1,500. Oh, but to get thickness, I need to divide by 2. So divide by 2. And so this is 2,550 nanometers thick. Maybe I'll move the decimal and call it 2.55 micrometers. So that's the first part of this problem. A, what is the thickness of it? Now, kind of at least conceptually, a throwback to our thermodynamics, if you warm this, it's going to expand. So if the alcohol is warmed until the thickest part turns from dark to light. So remember, the thick part is already this thick right here. And as we warm it up, it's going to get even thicker. And of course, getting thicker means that we have a longer path length now, and we are now going to get to this spot where we get bright light reflected. So it turns from a dark to a bright. What is the new thickness? So there's a couple ways we could do this. We could just use this equation if we so desired. I'm just going to do it more conceptually, and so I'll go delta T. In other words, how much did it get thicker by? See, because what I know is if it changes from a dark to a bright, then the extra distance it travels, okay, and so I'll call it 2 delta T. So it gets thicker by delta T. The light travels an extra distance then of 2 delta T, and that would have to be a half of wavelength in the alcohol, because that extra half wavelength is why we are going to go from a dark into a bright. So knowing that, I can solve for the extra thickness. So the extra thickness, as you can see, would be a quarter of a wavelength, because down and back would be an extra half a wavelength in the material. So this is the 465 divided by 1.55. So it comes out to be an extra 75 nanometers. So the new thickness, I think they asked for the new thickness, not how much did it get thicker by, right? Yeah. What is the new thickness? I need to add the 75 to the 2,550. So that would put it up to 625 nanometers, or 2.625 micrometers. And that would be the new thickness. Okay, good. So here's another one where B is the hardest one. So it looks like 1 and 2, B was pretty long and hard, and fortunately 3 and 4 were a little more direct. And so pace-wise, I'm doing really well here. All right, so this can lead us to the last problem on the exam. And it looks like it is a single slit from the picture here. A light of wavelength passes through a single slit width of onto a screen 2.5. What is the size of the central bright fringe? So just kind of reviewing, remember, the light would come out and spread out and make an intensity pattern that looks something like this, a sinc squared function. And this mound here is where most of the light is, and so most of the light is in this center part, the central maximum. And it's this first interference within the single slit where the m equals to 1, and over here the m equals, you might say, -1. But to find these dark places, we had the a sine theta equals an integer number of wavelengths in the material. Now, I think this is in air. It doesn't say one way or the other, so we can kind of just assume we're doing it in the laboratory, so it's in the air. And so I can set m equaling 1 to figure out where it is on the screen. And so let me just set m equal to 1, and so that would be a lambda. And I guess, again, this would be a, and the small angle approximation would make this a y over L. Solving for where on the screen is this dark spot, I would get lambda times L over A. And now I can put in my numbers. So in this problem, they say the wavelength is 525 nanometers. Times the distance to the screen, 2.5, divided by A, the width of the screen, which is 45 micrometers. All right. So according to this, we are looking at roughly 3 centimeters. 0.0292, and I've done everything in meters. Now it says the size of it, so it would be up and down the same distance. So let me double that to answer the question. So times 2 means I'm at 0.0583 meters for the size, or if you want it in centimeters, 5.83 centimeters for the size on the screen here. So whatever roughly 6 centimeters is, so about be that wide on the screen. Okay. All right, so there's A. That wasn't too bad. Oh, okay. It's going to be a little harder here. I see a lens. If a convex lens of a focal length of 50 centimeters is placed 30 centimeters from the slit, and so between the slit and the screen, what is the size of the central bright one? Okay, so this one's going to take a little more thought, but it's like the one we did earlier, which I guess was number 2, and a lot of our optics ones, where what do we do is when you have 2 optical elements, remember that the first one just redirects the light, and the image from the first one then becomes the object for the second one. So you might say that we have this lens and we have a screen. And before the lens, you know, we were just saying, well, the screen sees a single slit. And the distance away was 2.5 meters. But what's going to happen now is the light is going to enter the lens, get redirected, and so there's going to be an image of a single slit. So the good news is the screen is still going to see a single slit. The screen is still going to see an intensity pattern that looks like a sinc function squared. But where that single slit is located is going to be the image after the light gets redirected here. So what we need to do is 1 over P plus 1 over Q is equal to 1 over F. So for us, the object distance to the lens, I think they said 30, didn't they? The convex lens with a focal length of 50 is placed 30 centimeters from the slit. So this is a 30. And this is a 50. And so now we can figure out, and I'll draw it in green, where is that image. So 50 reciprocal minus 30 reciprocal. Take the reciprocal of that, and I get a number, I'll write it in green, of negative 75 centimeters. Okay, so negative would be on this side of the lens, and it would be way over here somewhere. So that's 75 centimeters. Maybe I'll write it as 0.75 meters, because all the way to the screen, remember, would be another 2.2 meters. And I'm subtracting off the 0.3 meters from here. Because remember, originally we were given that from the slit to the screen is 2.5 meters. So if I subtract off the 0.3 from this lens to the screen is 2.2 meters. And what the screen is now seeing is the image, which is this projection of 75. So you might call this the new L. I'll call it the L prime, if you will, because it would be then the 2.2 meters plus the 0.75 meters, which would make 2.95 meters. So there's our new distance. Now, if you got that much, good for you, but there's also then the new size of the opening. Because remember, there's the magnification. And so the light has been redirected as it goes through this lens. And so it not only appears to be coming from a new point, that's what the Q is, but it appears to be a different size, that's what the magnification is. So we're going to have to take the magnification times the original slit size. And the magnification would be the negative of the negative 75. That's the Q. So it's minus Q over a P times a 30. And the original size was 45 micrometers. All right, so grabbing my calculator, I've got the 75 divided by 30. So that's 2.5. And so the slit looks 2.5 times bigger. So it's further away and 2.5 times bigger. So less spreading because it's bigger, but more spreading because it's got a farther distance to travel. But let me take that 2.5 and multiply by the 45. And so that is 112.5 micrometers. Okay, so as far as the screen, let me just kind of summarize these. The screen is seeing light coming from a slit that is 2.95 meters away. That's what the lens had done to redirect the original. So it's no longer just the 2.5 meters. The lens is making it look like the light's coming further away. But it's also making it look like it's coming from a bigger opening. But the logic is still the same, that if you follow that same equation here, the y would be a lambda L over A. Now you might put primes here because they would be how they just been affected by the lens. All right, so putting in my numbers here, let's see, the wavelength was what again? 525 nanometers, I believe. Wavelength, 525 nanometers. The screen now is 2.95, and the A is 112.5 micrometers. So we're looking here at about 0.013, I'll call it 8. And of course, like before, double it. So times 2, and we've got a 0.0275 meters. And so about half the size. And I guess that hopefully makes a lot of sense, because as I said, the A is much, much bigger, and you're going to get less diffraction, less spreading out. Now, granted, it is further away, and I also said that that would tend to spread it out, give it a chance to spread a little bit more. But it's not that much of an increase in distance. 75 or 0.75 out of 2.2 is not that much. But this was a pretty big amplification. This was over 2. So this dominates it. Of course, you can also see it by, it's a convex lens, so the light was spreading out, and then it hit this lens, and so it would have spread out to here, and the converging lens isn't strong enough to make it converge, but it is strong enough that it would make it less divergent. And so we do expect the number to become smaller. And I guess I probably should have said that before we actually did the numbers. But it's nice to kind of read our numbers here again and just say, look, I do expect it to spread less, because this converging lens is designed that way. It's designed to keep it from spreading. Or if it's strong enough, actually change it from spreading to converging. All right, well, hope all that helped, and that would be the exam. So we got some extra time to double check it and scan it and turn it in on Canvas. Take care.